Hello there. Today we are going to discuss pushdown automation, which is a part of the formal language automata theory for our in-semester exam 2. Our team includes Shreyash, Devang, that is me, Akanksha, and Vaishnavi. Before we start with pushdown automation, let us first look at the automata classes. Study of automata is the study of languages. How do you create a system that will detect the highest number of strings, highest number of languages can be defined within that? That is the study of automata. The first one of it is the combinational logic, which is the most basic one. Second is the finite state machine, and then the topic that we are going to discuss, the pushdown automation, and finally the most powerful, Turing machine, defined by Sir Alan Turing. So a few words about combinational logic. As we had studied the Boolean equations by George Boole, combinational logics are the digital circuits about the AND gates, NOR gates, NOT gates, etc., where the states define the output. They don't store any memory. Similarly, finite state machine would store the current state, and using the current state, they would give you where to proceed, whether you go to a final state or whether you get stuck at the dead end. Uh, Both of these systems have limitations. The biggest one being that they lack memory. Their output will be determined using the current state, but not of their previous, and that's why some cases like palindromes they cannot recognize that, which is why there is a need for a better system. Say hello to pushdown automata. Pushdown automata utilizes a stack. It helps us to store the data, it helps us to store the previous states and then use them. This is more capable than finite state machines, but it still lacks, and therefore it is less capable than Turing machines. They are used to implement a more powerful thing called the context free grammar, which we are going to discuss shortly. The structure is similar to the finite state machine in that if we see the diagrams, we can plot the pushdown automata inside a finite state machine diagram as well. Even they have deterministic and non-deterministic forms. Let's discuss context-free grammar for a second. Context-free grammar are all the patterns that can be created. Their structure is a four-tuple, the VTPS. The starting point, the terminal, the set of all terminals, the set of all non-terminals, and the production states. What we see here are the production states. We start by the starting point, and then we keep defining the non-terminal points and terminal points till we reach a string that doesn't have a production inside it. Now let us see the informal definition of the pushdown automata. What we see here is a machine that is parsing a string and is making use of the stack. For every element that it encounters, it has four options. It can either pop from the stack, push to the stack, or replace the top, or do nothing at all. Using this, we can either find the success or the dead state of a particular string belonging to a language. One thing to note here is that because of the stack memory, it can parse strings of infinite size. Now let us look at the difference between deterministic and non-deterministic pushdown automata. In deterministic automata, it can only have at most one legal transition for the same combination of input symbol, state, and top stack. Meanwhile, for non-deterministic, it can have either zero or multiple. Deterministic pushdown automata is used in parser design, while non-deterministic is used for syntactic compiler design. Other than compiler design, the applications include arithmetic evaluations, where, as we know, arithmetic evaluations are passed from left to right, making use of the stack, and other stack applications, may it be recursion or any such.
Now that we have basic idea of push-down automata, let's look at its formal definition. So push-down automata is defined using a seven tuple as specified here. Here Q is a finite set of states. Summation is the finite set of input alphabets that the strings of the language will be comprised of. S is the finite stack alphabet, and then we have a transition function. Q naught is the initial state, I is the initial stack symbol, and F is the set of accepting states or the final states. So now let's see how transition function is defined in a pushdown automata. So here arguments are in form of a triple, that is q, a and x, where q is a state, a is the input alphabet, it can also be an empty string, and x is the symbol at the top of the stack. Here output is a finite set of pairs, that is p and gamma, where p is a new state and gamma is a string of stack symbols that will be replaced at the top of the stack. Basically, they will be pushed to the stack. Now let's see its graphical representation. In case of finite state automata, we have the initial state represented by a circle and a final state represented by double circles, and the transition represented by an arrow and the input alphabet written over it. So this is same in case of pushdown automata, just that the input and the statement associated with the stack is written in addition. Let's see how it is. So here 0 is an input symbol, A is a symbol on the top of the stack which will be popped, and B is the symbol that is to be pushed on the stack. Here if A is epsilon, that is a notation of an empty string, then nothing will be popped out, only push operation will take place. Similarly, if B is epsilon, then only pop operation will take place. So this will be more clear with an example. Here we have designed a pushdown automata to accept a language whose strings will be in form of 0 raised to n and 1 raised to n, where n is greater than or equal to 0. So basically the number of zeros will be same as the number of ones. Now here is the initial state q naught, and then we start reading the string and we push the first element in the stack as z. So this element is going to keep a record of the end of the stack. So whenever we encounter z, we know that we have reached the end of the stack. So whenever it reads 0, it's going to push 0 into the stack, and when the series of ones start, we are going to pop the zeros from the stack. So this is the main logic behind this automata. All the zeros pushed will be eventually popped out of the stack, and in this way we can keep a record that the number of zeros and ones will be equal in the string. So as we encounter z, that is when all the zeros will be popped, will also pop out z, and then we'll eventually reach to the accepting state.
So now we have seen definition and graphical representation of pushdown automata. Now we will see equivalence of context-free grammar and pushdown automata. First, we will see it from context-free grammar to pushdown automata. We know that pushdown automata is used to accept the languages generated by context-free grammar. The language generated by context-free grammar and the language accepted by pushdown automata actually belong to the same class of languages. So what our theorem says, a language is context-free if some pushdown automata recognizes it. A language is considered as context-free language if and only if any pushdown automata recognizes it. So part 1 of our proof is we are going to prove it from a given CFG, and we are going to show how to construct a PDA that recognizes it. So here we are considering one given grammar. It is an example. It says S gives B S and also A gives 0A and also E, and B gives BB1 and also 2. So what we are going to do, we are going to create one PDA from this grammar by using construction method. In construction, we are going using leftmost derivation form. In leftmost derivation, what we do is we check the leftmost non-terminal of the string and we expand it until we reach the required string. So we are starting with S symbol, which is the starting symbol. So we have S, and for this S we have here one rule which says S gives BS and also A. So instead of S we are writing it as a BS. So now in this string the leftmost non-terminal symbol is B. So We have one rule for B which says B gives BB1 and also 2. So instead of B, we are writing BB1 and S is written as S. So now in this string, the leftmost non-terminal symbol is B. For this B, we have this rule BB1 and it also gives 2. So instead of BB1, now we are writing 2. So instead of B, we have written 2. The string is now 2B1S. Now the leftmost non-terminal symbol is B. And here also we are writing 2 for this B. So our string now becomes 2 to 1S. Now our leftmost non-terminal symbol is S. And for S we have rule which says S gives BS and also A. So instead of BS we are writing A here. So now instead of S we have A. So now our string becomes 2 to 1A. Now for A we have here another one rule which is A is now our leftmost non-terminal symbol. So for A we are writing it gives 0A and it also gives epsilon. So instead of A we have written epsilon. So now we have 2 to 1 epsilon which is finally 2 to 1 which is the leftmost derivation expression. Here there is no non-terminal symbol. So we have reached the required step. So now how to represent it in PDA? So how to construct this using a PDA? So for this we are considering one general form. In this general form we have here terminal input and rest of the symbols that are yet to be considered. In terminal we have AAAA and in rest of the symbols we have DABC. Let's consider it is our PDA. Here are terminal inputs and here is rest of the symbol that are yet to be scanned. So we know that in PDA we have one stack. So we store this rest of the symbol on the stack. So here it is our PDA. Here are the inputs and we know that terminal inputs are, we assume that terminal inputs are scanned and rest of the inputs are yet to be scanned. So we store that on this stack. Z0 is the bottommost element of the stack and Z0 is used for when we reach the end of the stack. So here I have tilted this stack just for the understanding purpose. So in leftmost derivation expansion, we know that the every expansion we get, it is known as the left sentential form. So in such one left sentential form, I got this AAA and on stack we have BABC. So what we have to do now to convert this to PDA using, so first we have to match stack top to a rule. So our top of the stack is B. So we have considered one example here which says B gives ASA XBA. Now our B top of the stack matches with the rule. So what we have to do? We have to pop stack. So we have popped the stack and then what we have to do? We have to push right hand side of the rule on the stack. So our right hand side says ASA XBA. So we have pushed our right hand side on the stack. So here our stack now becomes ASA XBA and ABC were already in the stack. So here I have one transition diagram for this. Here it's the first state and it is the final state. In between here it is epsilon, the inputs which are not advanced. Here A, in which what we do, we match the top and if it matches then we pop it and then we push the right hand side onto the stack. So how we push BCD onto stack? These are the states which we have to go through for pushing BCD. First we will push D, then we will push C and then we will push B. So finally the stack now becomes a BCD. Just remember the order we push is in reverse. First we have pushed D, then we have pushed C and then B, but the stack we get is BCD. Now this is our final PDA in which the first state represents, in first state we don't read any input, we don't push, we don't pop anything, we just push Z0 onto stack. Z0 is used to represent whenever the stack is empty. After that we push S symbol which is the starting symbol. We know that starting in any derivation we start with starting symbol S. So now our stack has S and Z0. Now we check the top of the stack. If the top of the stack matches with any of the rules, then we pop it and then we push the right hand side of the rule. Here are all the states mentioned in only one state. So now we have encountered the final state. In final state, what we do is we just pop Z0 and we get the final state. Hence, we have proved that a language is context free if some pushdown automata recognizes it. That is, our theorem is proved. We have constructed a PDF for given CFG.
Hello, my name is Shreyash and I am here to explain you about the equivalence between the PDA and the CFL. So I am going to explain you how to convert a PDA to its equivalent context-free language. So here's a PDA with initial state Q0 and final state QF, and there are many intermediary states P, Q and R and its transitions. So for converting into a CFL, we have to convert all those transitions to its productions in the grammar and the states to the non-terminals. So for constructing a CFL, there are two steps. Step 1 is simplify the given PDA, and step 2 is to build the CFG. So in our grammar there is a starting symbol S. So the starting symbol non-terminal will be AQ0QF. Here AQ0QF is the non-terminal which will give us all the strings required to go from Q0 to QF. So let's see the step 1 in simplifying the PDA. Step 1. The PDA should have only one final or accepting states. If the PDA has many final states, then we have to converge all those final states into a single final state by taking the epsilon move, in which we read the epsilon symbol. We don't pop anything, neither do we push. In this way, we convert all those final state into a single final state. In step 2, second point, the PDA should empty its stack before accepting any string. It means that our PDA accepts the string by the empty of stack method. So at the final state, we should empty all our stack symbols and go to the final state. So third point is, make sure each transition either pushes or pops. So if we have a transition which pushes and pops simultaneously, then we can break down into two different transitions. In the first transition, we read the symbol A, we pop X from the stack and we don't push anything. And in the second transition, we read epsilon, we don't pop anything and we push Y. Here we ensure that by simplifying the language, by simplifying the PDA, we keep the language of the PDA same. In the step 4, start with empty stack and finish with empty stack. So in the start of the PDA, our stack should be empty, and at the final end of the PDA also the stack should be empty. Okay, so and in between there may be many pushing and popping in the PDA, and all those intermediary operations should follow shouldn't violate the rule of underflow and overflow. That underflow means when we pop from the stack, when we pop from an empty stack, and overflow means when we push too many stack symbols, which will overflow our stack. Okay, we have seen that how to reduce a PDA, how to simplify the PDA. In this video, we will see how to construct a CFG from a given PDA. Here we have starting state P and the ending state Q. And the main idea is to find all the possible strings which will take us from the state P to the state Q. So we consider a non-terminal APQ, which corresponds to state P and Q, and and which uh, and which gives all the strings which will take us from the state P to the state Q. Initially, we read a alphabet A and push Z into the stack and reach to the state R. In middle, we may push or pop many times and we reach to the state S. And then we read a symbol B and pop Z from the stack and reach state Q. Here note that the symbol initially which is pushed into the stack and the symbol which is popped from the stack is the same. So here we can see the strings are A dot 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 and B. So the middle string is that string which will take us from the state R to the state S, and that can be represented by the non-terminal capital A RS, which generates all those strings which will take us from the state R to S. So we have a production rule APQ gives small a, capital A RS and B. So if we have a PDA like this case 1, we can construct a production and add this to our grammar. So in case 2, we have to go from the state P to state Q. At P, A symbol is read and W is pushed into the stack. But W gets popped out somewhere in the middle before reaching the state R. And Z is pushed into the stack somewhere in the middle. There are also some other push and pop operation going on in the middle. And before reaching the state Q, we read the symbol B and we pop out Z from the stack. Here remember that the initial push symbol is different from the final popped out symbol Z. So we have to find all those strings which will take us from the state P to state Q, and those strings will be concatenation of the strings which will take us from the state P to R and from R to Q, and those strings can be represented by the non-terminal APR and ARP. These non-terminal runs will generate the required strings, and thus we have a production APQ gives you APR and ARQ. There are some other things that we need to take care of. If you have a self loop in your PDA, then how to generate a production. So if you have P, if you have state P and a self loop, then add the production APP gives you epsilon. If the and for the starts and for your start symbol in your grammar, add AQ0QR because AQ0QR non-terminal generates all the strings which will take you from the state Q0 to state QA. And this is how we can convert a context-free language from a given PDA. And in the last videos, Akanksha has shown you how to convert a context-free language to a PDA. And in this, I have shown you how to construct a PDA, how to construct a CFL from the PDA. Thus, PDA and CFL both are equivalent. So the classes of language accepted by the CFL and PDA are the same or equivalent. Thank you.